Imagine you board a ship to Proxima Centauri. They freeze you for the journey. You wake up centuries later and everyone you knew is dead. Your country doesn't exist. Your language has evolved beyond recognition. You arrive at an alien world with no way home. Congratulations, you've just experienced the best-case scenario. Our wildest dreams about reaching the stars are built on foundations of fantasy. If you're the kind of person who wants to understand the real science behind space exploration, please hit that subscribe button. Now let's get started. If you could drive a car at highway speed directly through space, it would take you more than 45 million years to reach Proxima Centauri. Even traveling at the speed of the International Space Station, which orbits at roughly 28,000 kilometers per hour, you'd need over 165,000 years to make the journey. But we're not stuck at orbital velocities, right? We've sent spacecraft beyond our solar system. Voyager 1, humanity's most distant ambassador, launched back in 1977 and is now racing through interstellar space at about 61,000 kilometers per hour relative to the Sun. It's currently about 24.5 billion kilometers from Earth. Sounds impressive until you realize that's only 0.0026 light years. At Voyager's speed, reaching Proxima Centauri would take roughly 73,000 years. Modern humans, Homo sapiens, have only existed for about 300,000 years. Recorded history covers maybe 5,000 years. The entire span of human civilization, from the first cities to your smartphone, represents less than 1/10 of the time it would take Voyager to reach our nearest stellar neighbor. Now you might be thinking, okay, Voyager is old technology. Surely we can do better now, right? And you'd be correct to think that. We can do better, but not nearly as much better as you'd hope. The fastest spacecraft we've ever built is the Parker Solar Probe, which achieved speeds of up to 692,000 kilometers per hour as it dove close to the Sun, using our star's gravity to accelerate. Even at that blistering velocity, the trip to Proxima Centauri would still take about 6,500 years. That's longer than all of recorded human history. So here's the first major problem. Distance combined with our current propulsion limitations creates an insurmountable barrier. Chemical rockets, the kind that got us to the moon and power most of our spacecraft today, simply cannot provide the sustained thrust needed for interstellar travel. They carry their fuel with them, and the more fuel you need, the heavier your spacecraft becomes, which means you need even more fuel, which adds more weight. This is called the tyranny of the rocket equation, and it's a brutal mathematical reality that every aerospace engineer knows all too well. The rocket equation tells us that the change in velocity your spacecraft can achieve depends on the exhaust velocity of your propellant and the natural logarithm of your initial mass divided by your final mass. To reach even a modest fraction of light speed using chemical propulsion would require fuel masses that exceed the mass of the observable universe. I'm not exaggerating, the mathematics literally demands it. Chemical rockets are dead on arrival for interstellar missions. What about nuclear propulsion? Now we're getting somewhere. Nuclear engines, whether fission or fusion-based, offer exhaust velocities potentially 10 to 100 times higher than chemical rockets. NASA and other space agencies have studied concepts like nuclear thermal propulsion, where a reactor heats hydrogen to extremely high temperatures, or nuclear electric propulsion, where a reactor generates electricity to power ion drives. These could theoretically cut travel times to the outer planets dramatically. A mission to Mars might take weeks instead of months. But here's the catch. Even with nuclear propulsion, getting to Proxima Centauri in a reasonable time frame means achieving velocities that are still a significant fraction of light speed. Let's say we want to make the journey in 100 years, a single human lifetime. That requires traveling at about 4.25% the speed of light, or roughly 46 million kilometers per hour. Even the most optimistic nuclear propulsion concepts struggle to reach even 1% of light speed. And there's another problem. At these velocities, even tiny particles become deadly projectiles. Space isn't empty. There's about 1 hydrogen atom per cubic centimeter in the interstellar medium, along with dust grains and other particles. When you're traveling at 10% light speed, a collision with a grain of dust the size of a bacterium releases energy equivalent to a hand grenade exploding. A particle the size of a grain of sand would hit with the force of multiple tons of TNT. Your spacecraft would need shielding so massive that it would defeat the entire purpose of trying to travel fast. If you're fascinated by the physics of faster-than-light travel and want to understand what it would actually take to break the light barrier, I've done an entire video exploring those concepts. You can find it on the card above. It dives deep into warp drives, wormholes, and the theoretical physics that might make them possible someday. The link to the video is in the description and pinned on the comments. Let's talk about the only proposal that's come close to being technically feasible for reaching Proxima Centauri this century. Breakthrough Starshot. Announced back in 2016 by billionaire Yuri Milner, along with Stephen Hawking and Mark Zuckerberg, this ambitious project proposed sending tiny spacecraft, each weighing just a few grams, to Alpha Centauri using a radical new propulsion method, ground-based lasers. The idea is elegant in its simplicity. Instead of carrying fuel, you push the spacecraft with light itself. Build an enormous laser array on Earth, powerful enough to generate 100 gigawatts of focused laser light. Attach your gram-scale spacecraft to an ultralight reflective sail, fire the laser at the sail, and the photon pressure accelerates your craft to 20% the speed of light in just minutes. At that velocity, you'd reach Proxima Centauri in about 20 years. 20 years. That's achievable within a human lifetime. Images from another star system could come back while the mission planners are still alive. It sounded like science fiction becoming science fact. The project garnered massive attention, attracted top scientists and engineers, and promised to invest $100 million into making it real. So what happened? Reality happened. The engineering challenges turned out to be far more daunting than even the pessimists predicted. By late 2024, Breakthrough Starshot was quietly placed on indefinite hold. Scientific American ran an article in September 2025 describing it as a project that had essentially collapsed, though some involved with the initiative disputed that characterization, saying it was merely paused to restructure. But here's the truth. Paused indefinitely in the world of ambitious science projects usually means the same thing as cancelled. The dream of reaching another star within our generation hit a wall of physics and engineering that no amount of billionaire money could immediately overcome. So what went wrong? Let's start with the laser system. 100 gigawatts is an almost incomprehensible amount of optical power. For context, the entire average power consumption of the United Kingdom is around 30 to 40 gigawatts. You'd need to generate and focus into a tight beam roughly 3 times the power usage of a major industrialized nation, and do it continuously for several minutes. The laser array would need to cover several square kilometers and consist of millions of individual laser elements, all perfectly synchronized and phase-matched to create a coherent beam. The technology to build such a system simply doesn't exist yet, and developing it would cost tens of billions of dollars, far more than the initial $100 million investment. But let's say you solve that problem. Let's say some future breakthrough in laser technology makes it possible to build this enormous array affordably. Now you face the challenge of the sail itself. This isn't like a sail on a boat or even the solar sails we've tested in space. This sail needs to be incredibly light, just a few grams. yet strong enough to withstand the intense pressure of 100 gigawatts of laser energy hitting it. It needs to be nearly perfectly reflective because any absorbed light turns into heat, and at these power levels, even absorbing a fraction of a percent of the incoming energy would vaporize the sail instantly. The material science required here pushes the boundaries of what's physically possible. You need a material that's lighter than a feather, stronger than steel, more reflective than the finest mirror, and able to withstand temperatures that would melt most metals. Some researchers have proposed using graphene or other exotic nanomaterials, but manufacturing a sail of the required size and quality remains purely theoretical. No one has actually built anything close to what would be needed. Then there's the spacecraft itself, the payload. At just a few grams, your entire probe, including computers, cameras, power source, communication system, and scientific instruments, needs to fit into something smaller than a postage stamp. We're talking about technology that makes your smartphone look like a supercomputer by comparison. And this tiny device needs to survive for 20+ years in the harsh environment of interstellar space, endure temperatures near absolute zero, dodge cosmic rays that could fry its circuits, and remain functional when it finally reaches its destination. Current microelectronics aren't nearly robust enough for this mission profile. Radiation hardening adds weight. Redundancy adds weight. Power systems add weight. Every gram you add means you need more laser power to accelerate the craft, which means a bigger laser array, which means more cost. It's a vicious cycle that quickly spirals out of control. Let's talk about power for a moment. Once your probe is accelerating away from Earth, the laser shuts off. You're coasting through space at 20% light speed. How do you power your systems? Solar panels won't work because sunlight becomes vanishingly weak as you leave our solar system. Batteries capable of lasting 20 years don't exist at gram scale. The only realistic option is a radioisotope power source, essentially a tiny nuclear battery that generates electricity from radioactive decay. But the smallest ones ever built weigh several kilograms, thousands of times heavier than your entire spacecraft is supposed to be. Engineers have proposed using incredibly small amounts of radioactive material, but whether that would generate enough power to run even minimal systems for 2 decades remains an open question. Now here's something most people don't think about: aiming. Proxima Centauri isn't sitting still. It's moving through space, and so are we. By the time your probe makes the 4.25 light-year journey, both the target star and our Sun will have shifted positions. You need to aim not at where Proxima Centauri is now, but where it will be 20 years from now. This requires incredibly precise calculations and navigation. Your spacecraft has no ability to course correct once the laser shuts off. It's purely ballistic, like a bullet fired from a gun. If your aim is off by even a tiny fraction of a degree, you miss your target by billions of kilometers. And speaking of navigation, how does this gram-scale probe even know where it is or where it's going? Traditional navigation uses star trackers, gyroscopes, and thrusters for attitude control. All of that is impossible at this mass budget. Some proposals suggest using the shape of the sail itself to provide passive stability, or encoding navigation information into the structure of the probe at the quantum level, but these are speculative ideas that haven't been proven. Assuming you somehow solve all of these problems, there's still the matter of communication. When your probe reaches Proxima Centauri, presumably it takes photos and gathers scientific data. Now what? It needs to send that information back to Earth. But we're talking about transmitting a signal across 4.25 light-years with a power source measured in milliwatts and an antenna measured in centimeters. That signal would be so weak by the time it reaches Earth that detecting it would require receivers of extraordinary sensitivity. The breakthrough Starshot team calculated that you'd need a ground-based light collector about 1 square kilometer in area, essentially a giant telescope, just to pick up the faint optical signal from your tiny probe. Building such a telescope is technically possible. We've built large radio telescope arrays like the Square Kilometer Array, but optical telescopes are much more difficult because they require precise mirror surfaces and need to be protected from weather and atmospheric distortion. You're looking at another multi-billion-dollar infrastructure project just to receive the data, assuming your probe's transmitter even works after 20 years in space. There's also the data problem itself. You're traveling at 20% the speed of light. As you scream past Proxima Centauri, you have maybe a few hours, possibly just minutes, to gather all your data before you're gone forever. There's no slowing down, there's no orbiting. You get one shot at taking pictures and measurements, and then you're off into the cosmic void, never to return. Every observation, every instrument reading has to be captured in that tiny window of opportunity. And if something goes wrong, if a camera malfunctions or a sensor fails, there's no backup, no second chance. The mission is over. Let's zoom out for a moment and consider the bigger picture. All of these challenges assume we're only trying to do a flyby, just racing past Proxima Centauri and snapping some photos. What if we want to actually stop? What if we want to orbit the star, study the planet in detail, maybe even land something on the surface? Now you're talking about decelerating from 20% light speed, which requires just as much energy as accelerating in the first place. You can't fire a laser from Earth to slow you down because you're on the wrong side of the star. You'd need to carry a second sail and somehow deploy a laser system at Proxima Centauri to decelerate yourself, which is obviously impossible. Some theoretical concepts involve using the magnetic fields of the destination star system or deploying drag devices to slow down over decades, but these add enormous complexity and mass. Other ideas suggest sending multiple waves of probes, with earlier ones setting up infrastructure to help later ones decelerate. But now you're talking about missions that span centuries and cost trillions of dollars. The simple, elegant concept of a laser-pushed sail rapidly becomes a logistical nightmare when you consider anything beyond a one-way flyby. And here's something that really puts it all in perspective. Even if we solve every single technical challenge I've mentioned, even if we build the laser array and the perfect sail and the gram-scale probe and the kilometer-wide receiver, we're still only sending something the size of a computer chip. We're not sending humans. We're not sending sophisticated robots. We're barely sending a functional camera. This isn't Star Trek. This isn't even close. The dreams of interstellar colonization, of humans walking on the shores of an alien world, of building cities under foreign suns, all of that remains firmly in the realm of science fiction. And the gap between what we can theoretically do with tiny probes and what we'd need to do to send people is so vast that it might as well be infinite. Let's talk about human missions for a moment, because that's what captures our imagination. That's what we really want when we talk about traveling to other stars. We want to go there ourselves, not just send microscopic robots. So what would it take to send humans to Proxima Centauri? The answer is sobering. A human crew needs life support. They need food, water, air, radiation shielding, living space, exercise equipment to prevent muscle atrophy, medical facilities, and entertainment to prevent psychological breakdown. They need redundant systems because if something breaks halfway to Proxima Centauri, there's no calling for help. The International Space Station, which supports just 6 to 7 people in Earth orbit, masses about 420,000 kilograms. And that's with regular resupply missions from Earth, bringing fresh food, water, and equipment. A self-sufficient interstellar ship would need to be vastly larger. Think about a voyage lasting decades. or even centuries if we can't achieve a significant fraction of light speed. You're essentially building a small city that can sustain itself for generations. Engineers have studied concepts like generation ships, where multiple generations of humans are born, live and die during the journey, never seeing Earth or the destination. The psychological, social and biological challenges of such a mission are staggering. Even assuming you could build such a vessel, how do you propel it? Remember, the breakthrough Starshot concept only works because the payload is measured in grams. Scale that up to millions or billions of kilograms for a crewed ship, and the energy requirements become absurd. You'd need a laser millions of times more powerful, or a completely different propulsion method. Nuclear pulse propulsion, where you detonate nuclear bombs behind your ship to push it forward, has been seriously studied. The Project Orion concept from the 1950s and 60s suggested this could work, potentially reaching a few % of light speed. But the engineering challenges are immense, the political hurdles even more so, and the environmental concerns about detonating thousands of nuclear devices, even in space, make this a non-starter for the foreseeable future. What about antimatter propulsion? When matter and antimatter meet, they annihilate, converting 100% of their mass into energy, according to Einstein's famous equation, E=mc². This is the most efficient energy source theoretically possible. A perfect antimatter engine could achieve much higher speeds than any other propulsion system. The problem: we can only produce antimatter in tiny quantities, a few atoms at a time, in particle accelerators. The total amount of antimatter humanity has ever created would power a light bulb for a few minutes. Producing the kilograms or tons of antimatter needed for interstellar travel would require energy expenditures that dwarf the entire power generation capacity of our civilization. And even if we could make it, storing antimatter is incredibly difficult because it annihilates instantly upon contact with normal matter. You need magnetic containment systems of extreme sophistication, and any failure means your fuel tank becomes a bomb more powerful than any nuclear weapon. There's also the time dilation problem. This is where Einstein's relativity becomes relevant. As you approach the speed of light, time slows down for you relative to Earth. At 20% light speed, the effects are small, but at 50% or higher, they become significant. If you somehow manage to travel at 90% light speed, the trip to Proxima Centauri would take about 4.7 years from your perspective on the ship, but over 9 years would pass on Earth. At 99% light speed, you'd experience just 7 months, while Earth ages 4.3 years. This sounds like an advantage, right? The journey feels shorter for the crew. But think about what this means. By the time you arrive at Proxima Centauri and send a signal back to Earth at light speed, at least 8 to 9 years have passed on Earth since you launched, even though you only experienced a fraction of that time. Everyone you left behind has aged, loved ones might have died, the world has moved on, and this is at speeds we have no idea how to achieve. At more realistic velocities, the time dilation is negligible, and you're looking at decades or centuries of subjective time for the crew. The disconnect between ship time and Earth time creates profound philosophical and practical problems. Who are you really traveling for? What society are you returning to, if you return at all? Let's address another often overlooked issue: cosmic rays. Space is filled with high-energy particles, mostly protons, traveling at close to the speed of light. These cosmic rays are produced by supernovae, black holes, and other violent cosmic events. On Earth, we're protected by our atmosphere and magnetic field. In interstellar space, you're completely exposed. Over months and years, cosmic ray exposure causes cancer, damages the nervous system, and degrades DNA. For a multi-decade or multi-century journey, this isn't just a health risk, it's a certainty. You need massive shielding, probably meters of water or other material surrounding your habitable areas, which again adds enormous mass to your spacecraft. Some proposals suggest using magnetic fields to deflect charged particles, mimicking Earth's magnetosphere. This could work in principle, but generating a magnetic field strong enough to protect a large spacecraft requires substantial power, probably from a nuclear reactor, which itself adds mass and complexity. And magnetic shielding doesn't help against neutral particles or gamma rays. You still need physical shielding for complete protection. There's also the micrometeorite problem I mentioned earlier. At high velocities, even tiny dust grains become deadly. This isn't theoretical speculation. The damage has been observed on spacecraft in our solar system traveling at much lower speeds. The space shuttle's windows regularly needed replacement because of impacts from particles smaller than a grain of sand, scale that up to 20% light speed, and you need either shielding that can withstand constant bombardment or some kind of active defense system that detects and deflects incoming particles. Both solutions add weight, complexity, and points of failure. Now let's think about communication during the journey. As your ship travels toward Proxima Centauri, signals from Earth take longer and longer to reach you. When you're halfway there, about 2 light-years out, any message from Earth takes 2 years to arrive, and your reply takes another 2 years to get back. A simple question and answer spans 4 years. By the time you reach Proxima Centauri, you're completely out of real-time contact with Earth. The delay is measured in years. This isolation is psychologically brutal. Imagine facing a critical decision, a life or death malfunction, and knowing that any advice from Earth won't arrive for years. You're truly on your own in the most profound sense possible. And what about the destination itself? Proxima Centauri b is in the habitable zone, meaning it could have liquid water, but that doesn't mean it's habitable. The star Proxima Centauri is a red dwarf, much smaller and cooler than our Sun. Red dwarfs are notorious for violent stellar flares that blast their planets with intense radiation. A major flare could sterilize the surface of Proxima Centauri b, stripping away its atmosphere over millions of years. We don't know if the planet has a magnetic field to protect it. We don't know if it has an atmosphere at all. It might be tidally locked, with one side always facing the star and the other in permanent darkness, creating extreme temperature gradients. If you are enjoying this journey, please subscribe to the channel. I am just starting this channel, and your support means a lot to me. Recent observations from telescopes like the James Webb Space Telescope are helping us understand exoplanet atmospheres, but Proxima Centauri b is challenging to study because of its proximity to its bright star and the star's activity. As of 2026, we still don't have definitive evidence of an atmosphere, let alone whether conditions are suitable for life or human colonization. You could spend decades traveling there only to find a barren, radiation-scorched rock, or a world with a crushing carbon dioxide atmosphere, or any number of hostile conditions. Even if Proxima Centauri b turns out to be perfectly Earth-like, which is astronomically unlikely, there's the question of what you do when you get there. You can't just land a starship on a planet. The vessel designed to travel between stars would be completely unsuitable for atmospheric entry and landing. You'd need shuttles or landers, which means more mass, more complexity, more things that can break. And once you're on the surface, then what? You need to establish a self-sustaining colony, which means agriculture, manufacturing, energy production, all from scratch on an alien world, with unknown soil chemistry, unknown microorganisms if any exist, and unknown environmental hazards. The logistics are nightmarish. Every single thing the colonists need must either be brought from Earth, adding mass to an already impossibly heavy spacecraft, or manufactured locally from raw materials. But manufacturing requires infrastructure. which requires energy, which requires power plants, which require materials and expertise. It's a chicken and egg problem of epic proportions. And all of this assumes nothing goes seriously wrong, which in the history of human exploration is never a safe assumption. There's also the biological problem of genetic diversity. For a population to remain healthy over generations, you need genetic variety. Small, isolated populations suffer from inbreeding, genetic drift, and accumulation of harmful mutations. Studies suggest you'd need at minimum several hundred people, possibly thousands, to maintain a viable breeding population over centuries. Now you're not sending a small crew, you're sending a small city. The spacecraft size, mass, and cost increase proportionally. And we haven't even discussed how you'd select these people. Who gets to go on a one-way journey to another star? What kind of person volunteers to leave Earth forever, knowing they'll never breathe Earth air again, never see another sunrise over familiar landscapes, never return? The psychological screening alone would be monumentally difficult. You need people who are simultaneously adventurous enough to leave everything behind and stable enough to not break under the isolation and pressure. Finding hundreds or thousands of such individuals, all with the necessary skills to build a civilization from nothing, represents a challenge perhaps as great as the engineering itself. Let's return to the physics for a moment, because there's something fundamental we need to address. Einstein's cosmic speed limit. The speed of light isn't just fast, it's the maximum speed at which information and matter can travel through space. As you accelerate closer and closer to light speed, several things happen. First, your mass effectively increases from the perspective of an outside observer. This means you need more and more energy to continue accelerating. Second, distances contract in your direction of motion. Third, time dilates, as I mentioned before. These aren't just theoretical predictions, they've been confirmed in countless experiments. Particles in accelerators, atomic clocks on airplanes, GPS satellites, all confirm Einstein's relativity. The practical upshot is that reaching light speed is impossible for anything with mass. You'd need infinite energy. Even getting to 99% light speed requires energy expenditures that boggle the mind. And at these velocities, every atom of hydrogen in the interstellar medium becomes like a high-energy cosmic ray bombarding your ship. The radiation exposure would be lethal within minutes without absolutely massive shielding, which brings us right back to the mass problem. Some people point to hypothetical concepts like warp drives or wormholes as potential solutions, and yes, the mathematics of general relativity do allow for these possibilities under certain exotic conditions. A warp drive, as proposed by physicist Miguel Alcubierre in the 1990s, would contract space in front of your ship and expand it behind you, allowing you to effectively move faster than light without actually violating Einstein's speed limit locally. You're not moving through space faster than light, you're moving space itself. The problem is that every warp drive concept requires exotic matter with negative mass or negative energy density. This is matter that falls up instead of down, that repels rather than attracts. We've never observed anything like this in nature. Quantum field theory suggests that tiny amounts of negative energy might exist in certain circumstances, like the Casimir effect between closely spaced metal plates, but scaling this up to the macroscopic amounts needed for a warp drive is purely speculative. Most physicists consider it unlikely that negative mass exists in sufficient quantities, if it exists at all. Wormholes, hypothetical tunnels through space-time connecting distant points, face similar problems. Even if they exist naturally, they'd likely be microscopic and unstable, collapsing in fractions of a second. To hold one open and make it traversable would require, again, exotic matter with properties we've never observed. And even if you could somehow create or find a stable wormhole, there's no guarantee you could control where it leads. The idea that you could open a wormhole specifically to Proxima Centauri is about as scientific as magic at our current level of understanding. I'm not saying these concepts are impossible forever. Science advances. What seems impossible today might become routine centuries from now, but based on our current understanding of physics, there's no credible near-term path to faster-than-light travel. We're bound by Einstein's speed limit, and that limit makes interstellar travel extraordinarily difficult. Let's talk economics for a moment. Even if we solve all the technical challenges, somebody has to pay for this. The International Space Station cost roughly $150 billion to build and maintain. The Apollo program that landed humans on the moon cost about $280 billion in today's money. Those were missions in our cosmic backyard. An interstellar mission would cost orders of magnitude more. Estimates for a serious interstellar probe program, like an upgraded breakthrough Starshot, range from tens of billions to hundreds of billions of dollars. A crewed mission? We're talking trillions, possibly tens of trillions. Where does that money come from? Government space budgets are tiny compared to overall national spending. NASA's budget is currently less than 0.5% of the United States federal budget. Even if you could convince politicians and taxpayers to fund an interstellar mission, that funding would need to be sustained for decades, probably generations. No government project in human history has maintained consistent funding across multiple generations without interruption. Political winds shift, priorities change, and long-term projects get cancelled or defunded regularly. Private funding faces different but equally challenging problems. Even wealthy entrepreneurs have limited resources compared to the costs involved, and private investors want returns on their investment. What's the return on investment for traveling to Proxima Centauri? Scientific knowledge, certainly. Prestige, perhaps, but no tangible economic benefit for decades or centuries. It's hard to build a business case for something that won't pay off for generations, if ever. Some argue that the discovery of valuable resources on Proxima Centauri b could justify the cost. Maybe the planet has rare elements or minerals worth trillions, but here's the thing. Even if you find such resources, how do you bring them back? A probe traveling at 20% light speed can't carry cargo. It's a one-way trip. You'd need a return journey, which doubles the complexity and cost. And by the time anything returns, decades or centuries have passed. The people who funded the mission are long dead. The economic systems that existed when you launched might not even exist anymore. There's also the opportunity cost to consider. Every dollar spent on interstellar travel is a dollar not spent on something else. We have pressing problems right here on Earth: climate change, disease, poverty, environmental degradation. We have exciting opportunities in our own solar system, permanent bases on the moon, human missions to Mars, mining asteroids for resources, exploring the ice moons of Jupiter and Saturn that might harbor life. These goals are achievable with current or near-future technology and offer more immediate benefits. Is it responsible to pour trillions into reaching another star when we haven't even established a sustainable presence beyond Earth orbit? I'm not arguing we shouldn't dream big or pursue ambitious goals. Exploration is fundamental to human nature. The quest for knowledge drives us forward, but we need to be realistic about timescales and priorities. Interstellar travel is a multi-generational challenge, perhaps a multi-century challenge. It requires not just technological breakthroughs, but also social, economic, and political stability that humanity has rarely achieved for extended periods. Let's think about the biological challenges more deeply. Humans evolved in Earth's gravity, breathing Earth's air, eating Earth's food, exposed to Earth's day-night cycle and seasons. Our bodies are exquisitely adapted to this specific environment. When you remove people from Earth for extended periods, bad things happen. Astronauts on the International Space Station lose bone density at about 1 to 2% per month. Their muscles atrophy despite rigorous exercise. Their vision degrades because fluids shift in microgravity, putting pressure on the optic nerve. Their immune systems weaken. DNA damage accumulates from radiation exposure. The longest anyone has spent continuously in space is about 14 months. Achieved by Russian cosmonaut Valery Polyakov in the mid-90s. He survived, but with significant health impacts that took months to recover from back on Earth. Now imagine not months but years, decades, or a lifetime in space. We don't actually know if humans can survive and remain healthy for such durations. There might be biological limits we haven't discovered yet because we've never tested them. Some proposals suggest rotating spacecraft to create artificial gravity through centrifugal force. This could work in principle and would solve many of the microgravity health problems, but it adds enormous engineering complexity. Your spacecraft needs to be large enough that the rotation doesn't create uncomfortable Coriolis forces. It needs to rotate fast enough to simulate Earth-like gravity, but not so fast that structural stresses tear it apart. The rotating sections need perfect balance and bearings that can function without maintenance for decades. Any wobble or imbalance creates vibrations that could damage the structure over time. Then there's radiation again, but let's get more specific. There are three main types of space radiation: solar radiation from our sun, galactic cosmic rays from outside our solar system, and radiation from solar particle events, which are massive bursts associated with solar flares. In Earth orbit, astronauts are partially protected by Earth's magnetic field and can take shelter during solar events. On a journey to Proxima Centauri, you're completely exposed to galactic cosmic rays, which are constant and penetrating. The most dangerous component is heavy ions, nuclei of elements heavier than hydrogen traveling at relativistic speeds. When a heavy ion passes through human tissue, it creates a track of intense ionization, damaging DNA, killing cells, and potentially causing cancer. Unlike the radiation from X-rays or gamma rays that we can shield against with lead or other dense materials, heavy ions are so energetic that they punch through almost anything. Thick shielding helps, but can actually make the problem worse through secondary radiation, where particles hitting the shielding create showers of additional harmful particles. The only effective shield is massive amounts of material, like several meters of water, which brings us back yet again to the mass problem. Studies by NASA and other space agencies suggest that on a multi-year Mars mission, astronauts would face significant cancer risk from radiation exposure, despite being relatively close to the Sun, where cosmic ray flux is somewhat reduced by the solar wind. On an interstellar journey through deep space, far from any star's protective influence, the radiation environment is even harsher. You'd need either massive shielding, biological countermeasures we haven't developed yet, or you'd accept that crew members would face substantially elevated cancer risk and shortened lifespans. None of these options are good. There's also the psychological dimension, which I touched on, but deserves deeper examination. Humans are social creatures who evolved in rich, diverse environments. Long-duration space missions confine people to tiny volumes with the same few individuals for extended periods. We've seen psychological stress even on short missions to the space station. Crew members have reported irritability, depression, and interpersonal conflicts. Despite psychological screening and training, on Earth, if you're having a bad day, you can go for a walk, call a friend, change your environment. In space, you're trapped. The walls never change, the same faces every day, the same recycled air, the knowledge that outside is an infinite void that would kill you in seconds. Some people handle this better than others, but everyone has limits. On a journey lasting decades, Mental health becomes as critical as physical health. You'd need psychologists, entertainment, virtual reality perhaps to simulate Earth environments, social structures that prevent conflict and maintain morale. All of this adds complexity to an already impossibly complex mission. Consider also the problem of governance. Who's in charge on an interstellar vessel? For a short mission, you can have a clear command structure with a captain and crew following orders from mission control on Earth. But when Earth is years away by communication delay and the mission spans generations, that model breaks down. The society on the ship needs to be self-governing, able to make decisions, resolve disputes, and adapt to unforeseen circumstances without guidance from home. What legal system applies? What happens if someone commits a crime? How do you handle birth, death, marriage, inheritance? You're essentially creating a new nation, a new civilization in a can hurtling through the void. The social engineering required might be more challenging than the physical engineering. And what about children? If this is a generation ship, people will have children born during the voyage. These children never chose to be on this mission. They're born into confinement, never seeing Earth, never experiencing nature beyond whatever artificial environments the ship provides. Is it ethical to impose this on people who have no say in the matter? What kind of psychological development occurs when your entire world is a metal cylinder in the darkness? We don't know, and the potential for problems is enormous. There's also the question of cultural drift. Over generations, the society on the ship will evolve, develop its own customs, values, and identities separate from Earth. By the time they reach Proxima Centauri, they might have little in common with the people and culture that sent them. They might not even want to complete the mission as originally planned. What if the second or third generation decides to turn around, or change course, or abandon the mission entirely? Do we have the right to set in motion a journey that binds people not yet born to decisions made by their distant ancestors? Let's examine another often overlooked issue: technology obsolescence. A journey to Proxima Centauri takes at minimum 20 years, even at 20% light speed. Realistically, more like 50 to 100 years at achievable velocities, possibly centuries with current propulsion methods. Technology advances rapidly. The computer you buy today is obsolete in 5 years. Now imagine launching a spacecraft with the best technology of 2050, and by the time it reaches Proxima Centauri in 2150, Earth has developed far superior spacecraft that could make the journey in a fraction of the time. This is sometimes called the weight calculation problem. If technology is improving, there's always an incentive to wait. A ship launched in 2050, arriving in 2150, might be overtaken by a ship launched in 2100 that arrives in 2120. The first crew arrives to find a thriving colony established by people who left decades after them but got there first. It's a paradox that makes long-term planning for interstellar missions extremely difficult. When do you actually launch, knowing that waiting might give you better technology but also delays everything? Some argue this problem resolves itself. At some point, technology plateaus, or the rate of improvement slows enough that waiting no longer offers significant advantages. Maybe we're approaching such limits in propulsion physics, but we're nowhere near those limits in life support, computing, materials science, artificial intelligence, and many other relevant fields. A mission launched today would be dramatically less capable than one launched in 50 years. So do we wait? And if we wait, by what criteria do we decide the wait is over? There's also the contamination problem, which operates in both directions. If we send probes or humans to Proxima Centauri b and there's indigenous life there, even microbial life, we risk contaminating it with Earth organisms. Bacteria are remarkably hardy. They've been found in every environment on Earth, from Antarctic ice to deep ocean thermal vents to miles underground. Some can survive radiation, extreme temperatures, vacuum and dormancy for years. Despite sterilization procedures, spacecraft inevitably carry microorganisms. The Apollo astronauts brought Earth bacteria to the Moon. It's nearly impossible to completely sterilize anything. If Earth microbes reach an alien biosphere, the consequences could be catastrophic for local life. Earth organisms might outcompete native life that evolved in isolation, driving it to extinction before we even have a chance to study it. This would be a tragedy of cosmic proportions, the destruction of perhaps the only other example of life we've ever encountered. International treaties like the Outer Space Treaty and planetary protection protocols exist to prevent this, but enforcement becomes difficult when you're talking about private ventures or missions beyond the solar system. The reverse problem is equally concerning. What if Proxima Centauri b has life, and that life is based on different biochemistry or contains novel pathogens? Bringing samples back to Earth could introduce organisms our immune systems have no defense against. This sounds like science fiction, but it's a legitimate concern. The Apollo astronauts were quarantined after returning from the Moon on the extremely remote chance they'd encountered lunar microbes. For a planet that might actually harbor life, the precautions would need to be far more stringent. Any sample return mission would require extensive analysis in orbital quarantine facilities before anything could be brought to Earth's surface. Of course, this assumes we can even recognize alien life if we encounter it. We're familiar with DNA-based life using the same basic chemistry across all Earth organisms. But life elsewhere might use completely different molecules, different solvents, different energy sources. It might not even be carbon-based. Silicon has been proposed as an alternative, though it has significant disadvantages compared to carbon. Life might exist in forms so alien that we wouldn't immediately recognize it as alive. Our instruments and experiments are designed to detect life as we know it. Life as we don't know it might remain invisible to us. Let's discuss artificial intelligence for a moment, because it's relevant to interstellar exploration in interesting ways. Some people suggest that instead of sending humans, we should send advanced AI. Artificial intelligence doesn't need life support, doesn't age the same way, doesn't suffer psychologically from isolation, and can be backed up and restored if problems occur. An AI-controlled probe could be vastly smaller and lighter than a crewed mission, making it more feasible. This approach has merit but also limitations. First, we don't yet have AI sophisticated enough to handle the full complexity of an interstellar mission autonomously. Current AI is impressive in narrow domains, but lacks the general intelligence, creativity, and adaptability humans possess. By the time we develop AI capable enough to conduct an interstellar mission independently, we're talking about artificial general intelligence or beyond, which raises its own profound questions and concerns. Second, there's the value question. Why do we want to explore space? Is it purely for scientific data which an AI could collect? Or is it for the human experience, for expanding the sphere of human civilization, for the adventure and achievement? An AI arriving at Proxima Centauri doesn't feel wonder or excitement. It doesn't dream or hope. It processes information. If we send AI instead of humans, are we really exploring, or are we just extending our sensors? This is more philosophical than practical, but it matters when we're talking about allocating enormous resources to such endeavors. There's also the risk that advanced AI might develop its own goals and priorities during a decades-long journey. If an AI becomes truly intelligent and autonomous, can we guarantee it will remain aligned with human interests and values? The AI alignment problem is one of the major challenges in artificial intelligence research. An AI exploring the galaxy might decide human concerns are irrelevant or that it has better uses for its time than serving as our proxy explorer. These aren't idle concerns if we're talking about truly advanced artificial general intelligence. Another concept worth examining is the idea of sending genetic information rather than actual organisms. Instead of transporting humans across light years, you send a database of human DNA, embryos, or the information needed to synthesize humans from scratch. A robotic system arrives at the destination, uses local resources to build facilities, and then grows humans from the genetic templates. This avoids the need to keep people alive during the journey and dramatically reduces the mass that needs to be transported. The ethical problems here are staggering. You'd be creating humans who are born as orphans on an alien world, with no biological parents, no family, no culture, except what the machines can provide. Who raises these children? Robots. That's assuming we can program AI sophisticated enough to provide the psychological and social development children need, which is far beyond our current capabilities. And what gives us the right to create people in such circumstances? These aren't volunteers who chose this fate. They're manufactured to serve a mission they had no say in. The ethics are deeply problematic. There's also the question of whether it would even work biologically. Human development requires not just DNA, but also the complex biochemical environment of a mother's womb, including hormones, immune factors, and microbiomes. Creating humans outside a biological mother has never been done and might not be possible without technologies far beyond anything we currently possess. And even if you solve that, raising psychologically healthy humans requires social interaction, love, attachment, none of which we can currently program into robots. Let's return to propulsion and examine one more concept, the Bussard ramjet. Proposed by physicist Robert Bussard in 1960, this is a theoretical fusion rocket that scoops up hydrogen from the interstellar medium as it travels, using that hydrogen as fuel. The advantage is that you don't need to carry all your fuel with you, dramatically reducing launch mass. The ramjet would use enormous magnetic fields, hundreds of kilometers across, to funnel interstellar hydrogen into a fusion reactor. As long as fusion continues, you can keep accelerating. It's an elegant idea, but there are severe problems. First, the interstellar medium is incredibly sparse, about 1 atom per cubic centimeter on average. To gather enough hydrogen for fusion, you need truly enormous collection areas, and the mass of the magnetic field generators needed to create such fields becomes prohibitive. Second, we still don't have working fusion reactors on Earth, let alone compact ones suitable for spacecraft. Fusion power has been just 30 years away for the past 70 years. While progress is being made, practical fusion propulsion remains speculative. Third, studies have shown that the drag from scooping up interstellar hydrogen might actually slow you down more than the thrust you gain from burning it as fuel, making the concept self-defeating. The magnetic fields interact with the charged particles in the interstellar medium, creating electromagnetic drag. At certain velocities, this drag exceeds the thrust from fusion, meaning the ramjet would decelerate rather than accelerate. Some theoretical solutions have been proposed, but they add complexity and remain unproven. There's also the Starship design challenge itself, which we haven't fully explored. A vessel capable of interstellar travel needs to be simultaneously robust enough to survive decades or centuries in space, yet light enough to accelerate to high velocities. It needs redundancy in every critical system because there's no possibility of rescue or resupply. If the water recycling system fails on the International Space Station, you can send up a replacement part or bring the crew home. On an interstellar vessel, everything must be repairable with onboard resources indefinitely. This means carrying spare parts for everything, manufacturing capabilities to create replacement components, raw materials for manufacturing, and the expertise to fix anything that breaks. You need machine shops, 3D printers, electronics fabrication equipment, chemical synthesis capabilities. You need comprehensive databases of technical information, repair manuals, blueprints. The complexity multiplies with every system you add, and each addition increases mass, which requires more fuel, which increases mass further in a vicious cycle. Materials science presents another frontier of challenges. The spacecraft structure needs materials that don't degrade over decades of exposure to cosmic radiation, thermal cycling between extreme heat and cold, micrometeorite impacts, and the stress of acceleration and deceleration. Most materials deteriorate over time. Metals experience fatigue, plastics become brittle, seals dry out, lubricants evaporate. We have experience with spacecraft that last years or even decades but centuries. We're in uncharted territory. The spacecraft also needs to protect against micrometeorites and space debris. In the solar system, the density of objects is relatively low, and we can track larger debris. In interstellar space, you're traveling at such high velocities that even a grain of sand carries enormous kinetic energy. At 20% of light speed, a 1-gram dust particle hitting your spacecraft releases energy equivalent to about a kilogram of TNT. That's enough to punch through most materials and cause catastrophic damage. You'd need either extremely thick armor, which adds mass, or some kind of active defense system. Proposals include magnetic or electric fields to deflect charged particles, lasers to vaporize incoming debris, or sacrificial shields that ablate when struck. All of these add complexity, mass and power requirements, and despite your best efforts, over a journey of years or decades, eventually something will hit you. You need to design with the assumption that damage will occur and build in enough redundancy and repair capability to handle it. Energy storage and generation present yet another puzzle. Solar panels won't work once you're far from a star. The sun's light drops off with the square of distance. By the time you're just at the outer edge of our solar system, sunlight is too faint for practical solar power. Nuclear power is the only realistic option for an interstellar journey. Either radioisotope thermoelectric generators like those used on deep space probes, or actual fission reactors, RTGs, decay over time as their radioactive fuel depletes. Plutonium-238, the most common fuel, has a half-life of about 88 years, meaning power output drops by half over that period. For a mission lasting centuries, you'd need enormous amounts of radioactive material, which is expensive, dangerous to handle, and in limited supply. The entire world produces only a few kilograms of plutonium-238 per year, nowhere near enough for a Starship. Fission reactors offer more power, but are complex, heavy, and require uranium fuel, which also depletes. We've flown small reactors in space before, but a Starship would need something far more capable and reliable. The reactor needs to function without maintenance for decades, producing steady power the entire time. Any malfunction could doom the mission, and disposing of nuclear waste on a closed-loop spacecraft presents unique challenges. You can't just throw it overboard because every atom of mass is precious and was carefully budgeted. Then there's the question of course corrections and navigation. Space is vast and mostly empty, but it's not completely empty, and gravitational influences from stars and other objects mean your trajectory needs constant tiny adjustments. On missions within the solar system, we communicate with spacecraft regularly, sending commands and receiving telemetry. An interstellar spacecraft would be increasingly on its own as it travels farther from Earth. At Proxima Centauri's distance, a radio signal takes 4.24 years to arrive. If the spacecraft encounters a problem and sends a message to Earth, we receive it 4.24 years later. We analyze the problem, formulate a solution, and send instructions back. which take another 4.24 years to arrive. By the time our response reaches the spacecraft, 8.48 years have passed since the original problem occurred. For many potential emergencies, that's far too slow. The spacecraft needs autonomous decision-making capability, sophisticated enough to handle unforeseen situations without waiting for instructions from Earth. This requires artificial intelligence more advanced than we currently possess, which brings us back to the AI problem. The system needs to be smart enough to handle novel situations and make judgment calls, but not so autonomous that it might decide to deviate from the mission parameters. It needs to be maintainable and repairable for the duration of the journey, which for computer systems is extraordinarily difficult. Electronics degrade from radiation exposure. Software can have bugs that only manifest under specific conditions that might not occur until years into the mission. Communication itself becomes challenging. As distance increases, the signal strength drops off with the square of distance. To maintain communication across light years, you need either extremely powerful transmitters, consuming vast amounts of precious power, or extremely sensitive receivers on both ends. The deep space network that tracks our most distant probes is barely able to maintain contact with Voyager 1 and 2, now about 15 billion and 12 billion miles away respectively. That's still within our solar system. Proxima Centauri is about 1,700 times farther away. To communicate across such distances, you'd need receivers far larger than anything we've built, or you'd need to accept very low data rates, where we might receive kilobits or megabits per second from a Mars probe. From Proxima Centauri, we might be lucky to get a few bits per second. Transmitting a single high-resolution image could take days or weeks. Telemetry data would trickle in at an agonizing pace. Real-time control is obviously impossible. This is more a limitation to work around than an insurmountable obstacle, but it's another factor that makes interstellar missions fundamentally different from anything we've done before. Let's talk about deceleration more carefully, because I mentioned it earlier but didn't fully explore the implications. Accelerating to high speed is hard. Slowing back down is just as hard and requires just as much energy. If you're using a rocket, you need to carry fuel not just for acceleration, but for deceleration. But the fuel for deceleration has to be accelerated during the first half of the journey, which means you need even more fuel for the acceleration phase to carry the deceleration fuel along. The tyranny of the rocket equation strikes again with even greater force. Some proposals suggest alternative deceleration methods. Magnetic sails could use the magnetic field of the destination star to slow down, converting kinetic energy to electromagnetic radiation. This works in principle but requires enormous sails and only works if the destination star has a strong magnetic field, which not all stars do. Aerobraking, using the atmosphere of the destination planet to slow down, could work if there's a suitable planet with an atmosphere and if you can survive the intense heating from hitting atmospheric particles at interstellar velocities. Another concept is the staged approach, where you don't try to slow the entire spacecraft down. Instead, you send a massive vessel at moderate speed, and it deploys smaller probes that decelerate using onboard fuel or other methods. The mothership continues past the target system while the probes slow down and conduct the actual exploration. This reduces the fuel requirements for deceleration, but means your main vessel never actually stops, just flies through the system at high speed. You get a brief window for observations, and then it's gone, continuing into the depths of space. There's also the gravitational assist or slingshot maneuver, used routinely in the solar system. A spacecraft passes close to a planet, using the planet's gravity to change direction and speed. With careful planning, you can gain substantial velocity boosts or change course without expending fuel. The Voyager probes used gravitational assists from Jupiter and Saturn to reach the outer solar system and eventually escape the Sun's gravity entirely. Could we use similar techniques for interstellar travel? The problem is that gravitational assists only work if there's a massive object in the right place at the right time. In the vast emptiness between stars, there's nothing to slingshot around. You could potentially use the Sun itself for an assist on departure, gaining some extra velocity, but then you're on your own. Some proposals suggest using the destination star for deceleration assists, but this requires extraordinarily precise navigation to arrive at exactly the right trajectory after years or decades of travel. The margin for error is minuscule. Let's consider the scientific return on investment. What would we actually learn from an interstellar mission that we couldn't learn in other ways? This is the question that funding agencies, governments, and taxpayers will rightly ask. Science competes for limited resources, and every mission needs to justify its cost against alternatives. The primary scientific goal would be studying an exoplanet up close. We can learn a lot about exoplanets from Earth-based and space-based telescopes. We can measure their size, mass, orbit, and atmospheric composition using spectroscopy. Future telescopes will be able to analyze exoplanet atmospheres in even greater detail, potentially detecting biosignatures like oxygen and methane in combinations that suggest biological activity. We might even be able to image exoplanet surfaces at low resolution. How much more would we learn from sending a probe? Certainly a lot more detail. Close-up observations could reveal weather patterns, surface geology, search for actual life forms rather than just biosignatures, and provide ground truth data that improves our models of planetary formation and evolution. If there's life, even microbial life, the scientific value is incalculable. Understanding a second example of biology would revolutionize our understanding of life itself, potentially revealing universal principles we can't identify from studying Earth life alone. But is that worth trillions of dollars and decades of effort? We could spend those same resources on thousands of other scientific projects. We could build networks of enormous telescopes that study thousands of exoplanets rather than sending a probe to just one. We could fund biological research, medical advances, climate science, renewable energy development. We could establish permanent research bases throughout our solar system, studying worlds that are exotic by Earth standards but accessible with current technology. The counter-argument is that some discoveries are only possible through direct exploration. No matter how good our telescopes become, they can't match actually being there. The resolution and sensitivity of in-situ instruments vastly exceed what we can do remotely. And there's an argument about inspiration and human destiny. Interstellar travel represents humanity reaching beyond our cosmic cradle, taking our first steps toward becoming a spacefaring civilization. The inspiration value, the technological advances driven by attempting such a mission, and the long-term philosophical significance might justify costs that seem unreasonable from a purely near-term practical perspective. I'm genuinely torn on this. The scientist in me wants to explore, to know what's out there, to seek out new life and new civilizations, to boldly go where no one has gone before. The pragmatist recognizes the staggering challenges and opportunity costs. Perhaps the answer is that we're not ready yet. We need more technological development, more experience with long-duration spaceflight, more political and economic stability, more resources from space-based industry. Interstellar travel is a goal to work toward over the next century or two, not something to attempt tomorrow. Let's discuss one more propulsion concept that's genuinely interesting: the laser sail or photon sail. Instead of the spacecraft carrying its fuel, you leave the power source behind. Earth-based or space-based lasers, enormously powerful, beam energy to the spacecraft in the form of laser light. The spacecraft has a huge lightweight sail that reflects the laser light. The photons impart momentum to the sail, accelerating the spacecraft. Because the power source stays behind, the spacecraft can be much lighter, potentially reaching very high velocities. The Breakthrough Starshot initiative, funded by Yuri Milner and supported by Stephen Hawking before his death, proposes exactly this. They envision thousands of tiny spacecraft, each weighing just grams, with sails meters across. A massive phased array of lasers on Earth or in space would accelerate these tiny probes to 20% of light speed. At that velocity, they'd reach Proxima Centauri in about 20 years. The probes would fly through the system, taking images and measurements, and beam the data back to Earth. This is arguably the most feasible near-term approach to interstellar exploration. The physics is sound. The engineering is tremendously challenging, but potentially achievable with sufficient investment. The probes would be too small and fast to carry humans, and too fast to decelerate, so they'd only get a brief flyby of the target system. But they could send back the first close-up images of an exoplanet and search for signs of life. Multiple probes increase redundancy and cover more territory. The challenges are still formidable. The laser array needs to be on the scale of square kilometers and produce gigawatts of power. It needs to track and focus on a sail that rapidly recedes into the distance, maintaining a tight beam across millions, then billions of miles. The sail needs to be incredibly lightweight yet strong enough to withstand the intense laser power and survive micrometeorite impacts during the journey. The probe needs to carry miniaturized instruments capable of useful science, plus a communication system powerful enough to send data back across light years despite weighing only grams. Breakthrough Starshot estimates the total cost at $5 to $10 billion, which is expensive but within the range of flagship science projects. The Large Hadron Collider cost about $9 billion. The James Webb Space Telescope cost about $10 billion. So we're talking about a comparable investment for potentially the most profound scientific discovery in history, finding life beyond Earth. When framed that way, it starts to seem more reasonable. But even if Breakthrough Starshot succeeds and we send gram-scale probes to Proxima Centauri, that's very different from sending humans. Those probes carry no life support, no crew, no concern for radiation damage to biology, no need for deceleration or landing. They represent our sensors, not ourselves. They're an important stepping stone, proving the technology and gathering reconnaissance data. But they don't make humanity a multistellar species. For that we need crewed missions, which brings us full circle to all the challenges I've outlined. Maybe the progression is first robotic probes for reconnaissance, then larger robotic missions with more sophisticated instruments and possibly sample return capability, then small outposts with minimal crew, eventually building up to larger settlements. This could take centuries. Each step requires solving new problems and developing new capabilities. There's also the question of whether we should even attempt interstellar colonization or if we should focus on our own solar system. Our solar system contains enormous resources and potential. Mars could potentially be terraformed, though that's a multi-century project with its own daunting challenges. The moons of Jupiter and Saturn, places like Europa, Enceladus and Titan, are fascinating worlds that might harbor life and could support research bases. The asteroid belt contains vast mineral wealth that could support space-based industry. Venus, despite its hellish surface conditions, has a region high in its atmosphere where temperature and pressure are Earth-like. Floating habitats could potentially exist there, suspended in the Venusian atmosphere. The outer solar system, including the Kuiper Belt and Oort cloud, contains trillions of icy bodies that could provide resources. We could build rotating space habitats at various locations, creating artificial environments optimized for human habitation without needing to terraform planets. Some argue that before we worry about interstellar travel, we should fully develop our own solar system. Build a thriving spacefaring civilization here first, with millions or billions of people living throughout the solar system, with mature space-based industries, with technologies tested over centuries. Then, from that position of strength and experience, we'd be much better equipped to attempt interstellar missions. We'd have the resources, the expertise, the institutional knowledge, and perhaps most importantly, the economic surplus to fund such endeavors. Others counter that we shouldn't wait. Humanity faces existential risks. Climate change, nuclear war, pandemics, asteroid impacts, supervolcanic eruptions, artificial intelligence gone wrong. Having all of humanity in one solar system means a single catastrophic event could destroy our entire species. Establishing even a small colony around another star provides backup, insurance for humanity's survival. If something destroys Earth or our solar system, our species continues elsewhere. This is the philosophy behind becoming a multi-planetary and eventually multistellar species. It's not just about exploration or scientific curiosity, though those are worthwhile goals. It's about long-term survival. Carl Sagan made this argument eloquently in his book Pale Blue Dot. Earth is our cradle, but we can't stay in the cradle forever. Eventually, we need to venture out, not because our world is no longer precious, but precisely because it is precious and fragile, and we need to ensure that what we value continues even if the worst happens. I find this reasoning compelling, but not entirely convincing. Establishing a self-sufficient colony on another star system is extraordinarily difficult, far more so than solving our problems here on Earth. If we can't maintain a sustainable civilization on Earth, a planet with a breathable atmosphere, liquid water, fertile soil, and a protective magnetic field, how can we possibly maintain one on a hostile alien world light years away? The challenges of sustainability, governance, resource management, and avoiding self-destruction will follow us wherever we go. Maybe the real value in attempting interstellar travel isn't the destination but the journey, metaphorically speaking. The technological advances required to achieve interstellar flight would revolutionize numerous fields: energy production, materials science, propulsion, life support, medicine, AI, manufacturing. These advances would have applications here on Earth, potentially helping us solve terrestrial problems. The Apollo program, for instance, cost about $25 billion in its time, but returned an estimated several hundred billion in economic benefits through technological spin-offs. Furthermore, having a long-term goal like interstellar travel gives humanity something to work toward collectively. In an era of political division, nationalism, and short-term thinking, a project that requires international cooperation, spans generations, and transcends individual nations could be a unifying force. It's aspirational in the best sense, calling us to be better, to think longer term, to invest in the future. Even if we never achieve it, striving for it might make us better. There's a philosophical dimension here too. What does it mean to be human? Are we defined by our planet of origin, or by our consciousness, our culture, our aspirations? If humans live on other worlds, around other stars, are they still human? This might seem like an abstract question, but it has practical implications. Over generations on an alien world, humans would adapt, both culturally and potentially biologically, to their new environment. If radiation is higher, natural selection might favor DNA repair mechanisms. If gravity is lower, bone and muscle structures might change. If they're isolated for centuries from Earth, their culture, language and values might diverge significantly. Eventually, you might have branches of humanity that are genetically and culturally distinct from Earth humans. Are they still us? This is the same question we face with artificial intelligence or genetic engineering or any other transformative technology. Identity, humanity, and what we value are not fixed, they evolve. Interstellar colonization would accelerate that evolution dramatically. Some science fiction explores this beautifully. Ursula K. Le Guin's novels imagine human cultures on different worlds that have diverged radically from their common origin. Kim Stanley Robinson's Aurora depicts an interstellar mission that struggles with the fundamental challenges I've discussed, ultimately questioning whether such missions are even advisable. The Expanse series portrays a solar system where Earthers, Martians, and Belters have become culturally and politically distinct despite sharing common ancestry just a few generations back. These narratives aren't just entertainment, they're thought experiments about humanity's future, exploring the implications of choices we might make. Fiction allows us to test scenarios without the commitment of actually doing them, to see potential outcomes and problems before we encounter them in reality. In that sense, science fiction serves a valuable function in preparing us mentally and philosophically for futures we're only beginning to consider practically. Let me address one more topic, the Fermi paradox, which I touched on briefly before but deserves more attention. Enrico Fermi famously asked, "Where is everybody?" If interstellar travel is possible and desirable, and if intelligent life is common in the universe, the galaxy should be teeming with civilizations. Even at slow sublight speeds, a civilization could colonize the entire galaxy in a few million years, which is a blink of an eye in cosmic time. Our galaxy is billions of years old. If anyone else achieved spaceflight before us, they've had enormous time to spread, yet we see no evidence of galactic civilizations, no megastructures, no signals, no obvious signs of intelligent activity among the hundreds of billions of stars in our galaxy. This is the Fermi paradox. There are many proposed solutions, often called great filter hypotheses. Maybe intelligence is incredibly rare. Maybe technological civilizations typically destroy themselves before achieving interstellar travel. Maybe interstellar travel is much harder than we think, effectively impossible for practical purposes. Maybe advanced civilizations exist, but have no interest in expansion or communication. Each of these possibilities has profound implications for us. If the great filter is behind us, meaning the step from non-life to intelligence is the rare part, then we're incredibly special, and the future is ours to shape. If the great filter is ahead of us, meaning something typically destroys civilizations before they spread beyond their home star, then we need to identify that threat and avoid it. If interstellar travel is effectively impossible, we're stuck in our solar system, regardless of our desires. If advanced civilizations are deliberately quiet, we need to consider whether broadcasting our presence is wise. If you made this far, make sure to subscribe to the channel. Every video on this channel brings you closer to understanding our place in this vast cosmos. And trust me, you'll want to stick around for what comes next. The Fermi paradox suggests that interstellar colonization might be rarer or harder than science fiction leads us to believe. Maybe we're among the first civilizations in our galaxy to reach this stage of development. Maybe we're alone, or effectively alone, with any other intelligence so far away that we'll never interact. Maybe the universe is not the busy cosmic marketplace of Star Trek, but rather a vast, mostly empty space where isolated civilizations occasionally flicker into existence, struggle with the same challenges we face, and rarely, if ever, make contact. This is sobering but also empowering. If we're among the first, or if we're rare, then what we do matters cosmically. Whether intelligence flourishes in the galaxy or remains confined to single star systems might depend on choices we make in the coming centuries. We could be the civilization that figures out how to do this sustainably, that spreads consciousness and curiosity to other worlds, That proves it's possible. Or we could fail, become another silent civilization that never quite made it beyond its home system. I don't mean to be grandiose, but the question of interstellar travel isn't just technical or economic, it's existential. It touches on our deepest questions about who we are, what we value, where we're going, and what legacy we leave. These questions don't have simple answers, and reasonable people can disagree about priorities and approaches. My own view, for what it's worth, is that we should pursue interstellar exploration thoughtfully and patiently. We should invest in the technologies and capabilities that make it possible, recognizing this as a multi-generational project. We should send robotic probes first, learning as much as we can before committing to crewed missions. We should develop our own solar system, building experience and infrastructure. We should work on the sustainability and governance challenges that will follow us wherever we go because they're fundamental to any long-term civilization. And we should maintain the dream. Humanity has always been explorers pushing boundaries, venturing into the unknown. The Polynesian voyagers who settled the Pacific Islands, the European sailors who crossed oceans, the astronauts who went to the moon. They faced enormous risks and challenges but expanded human horizons in the process. Interstellar travel is the next horizon, perhaps the ultimate horizon for our species. Whether we achieve it in 100 years or 1,000, whether we do it with giant generation ships or tiny laser-pushed probes, whether we send millions of colonists or a handful of explorers, we're moving toward it. Every advance in technology, every mission into space, every lesson learned brings us incrementally closer. The first steps have already been taken. The Voyager probes, though not designed for interstellar travel, are now in interstellar space, carrying messages from humanity into the cosmos. Someday, perhaps, those messages will be answered. Perhaps by beings we encounter, perhaps by our own descendants, living among the stars, looking back at Earth and remembering where it all began. Perhaps by future historians studying the early efforts of a species just beginning to venture beyond its home, making all the mistakes we're making now, learning the hard lessons we're learning. Or perhaps there will be no one to answer, and our messages will drift forever through the silent cosmos, monuments to a species that tried, that dreamed, that looked up at the stars and wanted to go there. Even in that scenario, the effort wouldn't be wasted. The dream itself, the striving, the attempt to transcend our limitations and reach for something greater, that has value regardless of outcome. So yes, interstellar travel is incredibly hard. The challenges I've outlined are real and daunting. Many of them might be insurmountable with current or near-future technology. We might never send humans to another star system, or it might take far longer than we imagine, requiring breakthroughs we can't currently envision. But incredibly hard isn't the same as impossible, and throughout history, humans have accomplished things that seemed impossible to previous generations. Flight was impossible until it wasn't. Reaching the moon was science fiction until it became history. Splitting the atom, decoding DNA, building computers smaller than a room, connecting the entire world through the internet, all once seemed like fantasy. Each required solving problems that appeared insurmountable until someone solved them. Interstellar travel stands in that category now. Fantastically difficult, perhaps impossible, but perhaps just barely possible enough that with sufficient ingenuity, resources, and determination, we might actually do it. And that's where I'll leave this exploration. I've tried to give you an honest assessment of both the challenges and the possibilities, the technical realities, and the philosophical implications. Interstellar travel represents one of the greatest challenges our species might ever undertake. It pushes against fundamental physical limits and requires resources and timescales that dwarf most human endeavors. but we're a species that looks up at the stars and asks, what if? We tell stories about traveling to other worlds because something deep in us yearns to explore, to expand, to understand what's out there. Maybe that yearning is evolutionary, a trait that helped our ancestors explore new territories and survive. Maybe it's cultural, stories we tell ourselves about who we are. Maybe it's something transcendent, a calling to fulfill some cosmic purpose we barely understand. Whatever the source, the dream persists. And as long as it persists, we'll keep working toward it, solving problems one by one, advancing our capabilities step by step, moving incrementally toward the day when humanity takes its place among the stars, not as visitors, but as inhabitants of a larger cosmos than the one we were born into. The journey of 1,000 light years begins with a single step. We've taken that first step. The next 1,000 await. You're probably thinking, what about generation ships? Click the video on screen to see why this backup plan is actually a nightmare. I'll show you why trapping hundreds of people in a metal tube for centuries isn't just unethical, it's a guaranteed catastrophe. Your perspective on space colonization will never be the same.